Hello guys, welcome back to another tutorial. Hit the bell icon button so that you don't miss out any tutorial.
Hello and welcome to this supplemental project for Unit 1 Linear Algebra, Scalars, Vectors, Matrices, and Tensors. In the first video, we covered the foundation and the basics of scalars, vectors, matrices, and tensors. However, now I want to dive into the actual application. How do you work and use these data structures in Python and NumPy? And that's exactly what we're going to be doing. So I'm going to be using Python, and I'm also going to be using Jupyter Notebooks. So if you haven't used Jupyter Notebooks in the past, it's a convenient way to develop Python applications that can be shared cross-platform and online. And you can do it right from your command prompt or terminal. So if you haven't installed Jupyter Notebooks or Jupyter Lab in the past, I'm going to go to my tutorial folder. You can install it assuming you have pip. Simply doing pip install Jupyter Lab with no space. If you click enter, that will install it there. Also for Python, I frequently use the Anaconda distribution, so you could do conda install Jupyter Lab, that will get it as well. And as long as you have pip or conda installed, which if you've worked with Python at all in the past, I'm very confident that you do, you can go ahead and install it that way. And once you get that all set up, opening up a Jupyter Notebook in this tutorial directory is as simple as typing Jupyter. I'm going to use Jupyter Lab actually, Jupyter Lab, and that'll open it up. You can pass other flags to this Jupyter command, such as IP. You could set an IP address. You could set a port. So there's different ways to use this Jupyter command if you are getting errors here. However, if everything's set up correctly, you should just be able to click enter, and this will pull up a Jupyter Lab notebook. And so this is going to open up in my Chrome browser. It opened up right here. And this is Jupyter Lab. Right now I have nothing in this tutorial directory, so over here there's nothing there because it's an empty directory. If you had files in this directory, they would show there. You have your launcher, so you can launch. I'm just going to do the Python default. Python default for my is going to be Python 2.7. However, we'll import that and print the version number in a second so we can verify that fact. Alright, so I'm going to rename this, give it something. Matrices would work well, that's what we're going to be working with. Alright, there we go. Alright, so if you weren't able to get to this step, go ahead and figure out what is going wrong with your Jupyter installation. I'm using Windows 10. And so everything that I do, you should be able to do. Sometimes the path variables can be messed up, so make sure Jupyter is in your path, and that is a common source of error. However, I'll assume that you've made it along with me, and let's keep going. All right, so here's what I want to do first. I want to import system, and I want to import NumPy. So NumPy is the fundamental package for scientific computing with Python, and we're going to use it to create and manipulate arrays. I'm also going to import it as MP, just since we're going to have to type it a fair number of times. And this is a frequent way that NumPy is shortened, so it's imported using this particular namespace. All right, then what I want to do is I want to print our version numbers here. So I'm going to print the string Python, and then I have the brackets. I can substitute a variable into these brackets using the .format command. So that's going to print the Python system version. And then I also want to print the NumPy version as well. So same thing, .format to substitute this version number into the string and print those out. All right, so you can go ahead and run Shift Enter. That will run this particular cell. Jupyter Notebooks is divided into cells, which you can run individually. All right, so there we go. Python 2.7. I'm on a Windows machine, 64-bit, and then NumPy I'm using version 1.14.1. All right, if you have an error importing these, you may not have NumPy installed, although you should if you have Python installed. So as long as these import statements work correctly, you should be good to go. All right, first things first, since we are supplementing the lecture scalars, vectors, matrices, and tensors, let's start by simply defining a scalar. So this is really simple. All you're going to do is x equals whatever number you want. Print x here to print this out. Shift enter when you run this, we get x is equal to 6. So in Python, a simple equal, you're going to assign a value to that particular variable. All right, now let's move on to defining a vector. So for a vector, I'm going to use a numpy array. So we have x is going to be equal to np, which is the namespace for numpy, which we imported above, np.array, and then we can simply pass the array to this. So I'll do 1, 2, 3. That will be my array. Print it out. And here we have a one-dimensional array, or a vector of 1, 2, 3. So as soon as you define things as a numpy array, you get helpful attributes that from this that you can print out. So we can say print, and we can do vector dimensions, and then do brackets because we're going to substitute in a variable. We'll say x.shape. So if it's a numpy array, you can simply type the name of the array and then .shape. Let's also print out the vector size. So that's another attribute that we can print out here. So x.size, just like that. So in these print statements, you can put these parentheses here, although you really don't need them in Jupyter Notebooks. So we print that out. We have a length 3. So with vectors, you'll typically hear it in length and not, for example, like dimensions. So length 3 and then a size 3, since we only have 3 parameters here. All right, so there's a vector. And that could be a vector of any length. You could add on to that if you wanted. So let's do a matrix. Defining a matrix. So x is going to be equal to np, and for this I'm going to use the dot matrix. You could use a dot array, it's just going to take some additional formatting. So we can pass now 1, 2, 3, let's say, and we're using the square brackets here to delineate rows from each other. 4, 5, 6 will be our next row, comma, and our last row, let's do 7, 8, 9. And then brackets on the outside of the entire matrix as well. And if we print this out, we now have a matrix, a 3x3 matrix with elements running from 1 to 9. But let's just go ahead and verify that. We can say print matrix dimensions. Let's go ahead and print these out. Dot format. And we'll say x.shape. Print matrix size. And we'll go ahead and do dot format. X.size. All right, there we go. And this should give us a 3x3, and in fact, it does. So we now have 2 indices, since we're working with a matrix here, and we have 9 elements in this matrix, and so we have a matrix size 9. 3x3, matrix size 9. And you can get this number simply by multiplying this by this. However many rows by however many columns you have will give you the size of your particular matrix. All right, and so a good thing about NumPy is that you can define matrices of any dimension really quickly. So of a given dimension, define a matrix of a given dimension. NumPy has a couple different commands, but one of them is going to be the numpy.ones. So this is going to make a matrix. It's going to be filled with the value 1. You could also do np.zeros will be a matrix of zeros. And then we can pass whatever dimensions we want. So if we want a 3x3, we can simply type a 3x3 there. Perhaps we wanted a 5x5. And now we have a matrix that's 5x5. We could keep going, making larger and larger matrices of any dimension that we want. If we take these guys, paste them down here, and run this now, you can see that it correctly has the size and dimensions that we want. If we bring this back down to 3x3, this will switch back to 3x3 size 9. So that's one of the valuable parts of NumPy, is you can define a matrix by its dimensions and then start assigning values to those dimensions afterwards. So the cool thing here is as well, we don't have to stop at the 2 indices. So we talked about tensors, which we're going to have a variable number of indices or axes. And so if we wanted to build a 3-dimensional tensor, we could simply add a dimension in our call to the NumPy here. And when we print this out, we now have a 3x3x3 tensor, which is going to be 3-dimensional tensor. And this is going to get harder and harder to visualize in Python. We're looking at 2-dimensional screens. However, you can keep going and add however many your heart desires. All right, so here we have 3-dimensional tensor. Let's take these guys and explore the shape and size a little bit. I'm going to switch this to tensor dimensions. We'll also have tensor size. If we print these out, we have a 3x3x3, which is going to give us 27 parameters. So one thing to notice is we went from a vector of 3, we added a dimension, we went to 9, add one more dimension, we go to 27. So we can see this is increasing exponentially. One thing to keep in mind as you add dimensions, you have an exponential increase in the number of parameters. So 27 parameters isn't hard for your computer to handle. However, you can start to get up into the millions and tens and hundreds of million parameters when you're working with artificial intelligence algorithms or deep neural networks. As a result, it's important to keep in mind that this number of parameters is going to increase exponentially. All right, let's move on to indexing a little bit. Indexing. All right, so we want to familiarize ourselves with NumPy's indexing conventions. So let's go ahead and define a matrix A. We'll do it NumPy 1s. We'll make it a 5x5. We can also pass a D type or a data type. We'll just make it integers. This decimal up here denotes that these are float values. If we do dtype.int, we will have integers, which we see here. Since there's no decimal, these are complete integer values. So there's our matrix, 5x5 matrix. And then, so indexing starts at 0. So for example, if we assigned a 0 and then let's do column 1, and we'll give it a value of 2, we see that that defines the index 0 row. So the first row, and this 1 here is going to be the second column, so we get a 2 there. And so here with just this equal sign, we're changing this value at this particular point to a 2, and then printing that off, and indeed we see that that's right there. All right, so there's that. Note that the NumPy uses rows, columns convention, and we can assign an entire row using this colon. So if we assign the all rows, and we'll do column 0, so the first column, we'll make this equal to 3. We print it off now. We can see that we assigned every single row, since we use this colon here, first column to the value 3. And we could also do that for all rows and all columns. All rows and all columns, maybe we want the values to be 5. If we print A, we now have all 5s. All right, so there we go. We can start adding dimensions. Let's go ahead and do that. So for higher dimensions, simply add an index. All right, A, let's do np.ones. So let's do a 5x5x5 here. So we have a 3-dimensional tensor. D type, we'll make it an integer. And then what I want to do is I want to assign first row a new value. So now indexing this, we're going to have 3 indices. So we have to have that there. We have 3. Let's make these a value of 6. Print A. We see we assign this all the way across. And again, the visualization gets harder and harder to do as soon as you start adding dimensions, but to the computer, it might look weird when we print it off. The computer is going to handle those just fine. All right, let's take a look at matrix operations really quick. So let's define, here, let's add a comment, matrix operations. If we have a matrix A, we'll do np.matrix. We'll write out the specific values here. So 1, 2 will be our first row, and then let's do 3, 4. So a simple 2 by 2 matrix. B, let's make just ones. So another 2 by 2. D type equals np.int. So there's those. If we run shift enter, that will store those to the variables. We can print A. We have our matrix. We can print B. We have our other 2 by 2 matrix B. All right, so we can do an element-wise sum. So C is going to be equal to A plus B. If we print C, we can see that we have added matrix B to matrix A, simple element-wise sum. We can do an element-wise subtraction. I apologize, should have some comments here. Let me add this up here. Element-wise sum. There we go. All right, so we have C is going to be equal A minus B. And we can just do it just as easily, subtracting 1 from all the values in A. Finally, matrix multiplication. It's as easy as typing A times B. If we print off C, here we go ahead and we get the matrix product of our matrix multiplication. All right. So there we have that. We can move on to the matrix transpose. Let's take a look at the transpose for a little bit. The matrix transpose, and again, this is probably going to be coming up more frequently than some of these other operations. So let me make a 3 by 3 matrix here. In NumPy, you can do a reshape, which comes in very handy. So if I just made a linear array, 0 through 9, I can reshape it as a 3 by 3. And now I have a 3 by 3 matrix with the values 0 all the way to 8. So there's that. Let's go ahead and calculate the transpose. So the transpose of A is really easy if this is a NumPy array or matrix. You simply do .t is going to give you the transpose of A. So if we print B, we see that we have switched the rows and the columns. We have flipped it along this main diagonal, and we now have the transpose. Taking the transpose of the transpose is going to give us our original matrix back, since we're doing the operation twice. All right, and let's look at some arrays of other dimensions. So if we had np.array, let's do range 10, and then A equals A.reshape. We'll do it 2, 5. Let's take a look at this. So we have a 2 by 5 matrix here. And then if we took the transpose, we could do B equals A dot T, capital T, if we print B. Again, we see we've switched the rows and the columns, taken the transpose. The main diagonal on this case runs from the 0 to the 6, so we're rotating along that, and it turns into a 5 by 2 matrix. And we can actually check that. If we print off B.shape, we see we got a 5 by 2 matrix now. So the transpose of a 5 by 2 is a 2 by 5 and vice versa. So rows and columns are switched in the transpose. All right, and last things, let's move on to tensors. So these are really easy for the computer to handle, more difficult for us to comprehend. Let's simply pass let's do a 10-dimensional. See if I can get these right. Tensor. So if you see how fast the computer can make that, let's print a.shape. We'll print the length of a.shape and also the print a.size. We print these out. So we have a 3 by 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 3 tensor, which is of course 10 dimensions. And you see how fast the number of parameters actually increase. We now have almost 60,000 elements in this tensor. So we are quickly getting larger. If we add an index here, we jump all the way to almost 200,000. So you can see how easy it is to produce a large number of parameters. All right, and so that is scalars, vectors, matrices, and tensors with numpy. So that should give you the basics to start setting up and working with these data types. Really easy to do in Python. And manipulating them is as simple as addition, subtraction, multiplication type operations. The transpose going to come up frequently in data pre-processing. And then tensors, oftentimes in deep learning, we are going to have a larger number of dimensions than 2 or 3. So we start working with tensors as well. All right, I hope you learned something.
Thank you for watching. Don't forget to subscribe to the channel. If you like the video, do give us a thumbs up and share it. Also check out amazing discounts and offers on our premium courses in the description below.